Hello everyone, and welcome to another video, where in this video, we are going to be looking at the central limit theorem in action, as well as learn how we can assess normality in R. When we are looking at the central limit theorem, it's not so much an R tutorial as it is just seeing how the central limit theorem works through simulation study. But then when we talk about normality, it will be an R tutorial. I will show you the function that you need to produce a normal probability plot, also called a QQ plot, a quantile-quantile plot. To begin, we'll just go over the central limit theorem. What the central limit theorem, often called the CLT, states is that if we have a large enough n, then it doesn't matter what distribution we are sampling from. The sampling distribution of the sample mean will be normal with mean mu and standard deviation sigma over root n, where that mu and sigma come from whatever distribution we're sampling from. This is an extremely powerful result and one of the most foundational results and theorems in statistics, because a lot of the time when we are doing statistical inference, we need to know the sampling distribution. And not only that, in a lot of instances, we actually need normality to be able to use a lot of these methods. So that's why it's so important that we not only have the central limit theorem, this extremely powerful result, but this also brings us to part 2 of this YouTube video where we will show you how to assess normality. Okay, right now we are in RStudio. A nice overview of what RStudio looks like and the different components in each of the quadrants is given in a previous video under the R Basics series. So if you are interested, please take a look at that. Otherwise, we are just going to give a bit of a refresher on generating random numbers. In this example, we are going to be generating 10 random values from the Poisson distribution. To do so, I'm first going to define a vector x, where my random numbers from the Poisson distribution will occupy. So from the Poisson, I want to generate 10 random values. And remember, the parameter that defines the Poisson distribution is lambda, and we will set that to be equal to 3. Oh, whoops. It's only supposed to be RPOIS. Okay, in our environment, we see that we have now generated 10 numbers. The Poisson distribution is a discrete distribution, which is evident in the numbers that were generated from it. Now, what happens when I take the mean? The value of the mean shows up down here in the console, and we see that the mean is 3.2. Now, what happens if I run this again? So I randomly generate 10 more, assign it to the vector x, and then take the mean. Now I get a mean of 2.5. Let's run that again. What happens? Now I get a mean of 3. The mean, or the sample mean, is dependent on the sample that we have. So this doesn't mean that, in general, the population mean of whatever distribution I'm setting here is 3.2 or 2.5 or 3 or whatever. These are all sample means, and they help us to estimate the population mean. But because these values depend on the sample, then we can treat the sample mean as its own random variable, and it has a distribution, the sampling distribution. And what we're going to do now is we're going to look at the central limit theorem in action. So whatever distribution we are sampling from, if n is large enough, then the sampling distribution of the sample mean will be normal with mean mu, whatever that mean is from whatever distribution we're sampling from, and standard deviation sigma over root n, where sigma is the standard deviation of whatever distribution we're sampling from. With the Poisson distribution, we have that the mean, by definition, is lambda, and the standard deviation is root of lambda. So our sampling distribution of the sample mean will be lambda and root lambda over root n. That is what we are expecting. And what we're going to do is we are going to generate a bunch of different samples from the Poisson distribution and plot the means so the sample means in a histogram. And then we will compare it to the normal distribution with that mean and standard deviation.
So we know where we are going, but how can we apply this in R?
What we want to do first is assign a set seed so that when we are generating numbers, this will stay consistent and we'll always get the same results. So if I set seed equal to 1, these results now become reproducible, and you can try these on your own as well. We want to generate a number of samples. We'll say we want to generate B samples. We want this number to be pretty big. Remember, we're going to generate samples from the Poisson distribution, take the mean of each one, and then visualize them with a histogram. In order for the central limit theorem to kick in, we need n to be large enough. And what that usually means is that n is greater than or equal to about 30. But for this first example, we're going to be a little bit cheeky and set n to be 5, very low. What we also need, since we're sampling from the Poisson distribution, is to define a value for the parameter lambda. And then finally, I want to define a vector for which we are going to store the values of the sample mean. Now that we have all of this, we are ready to start finding these sample means and storing them in our vector. The way that we are going to do this is by using a for loop. And there is another video where we talk about how to construct a for loop. We need a counter variable that in this case is going to go from 1 to b, because whatever we do inside of this for loop, we want to repeat that for each sample. The first thing we're going to do is generate n values from the Poisson distribution with parameter lambda equal 3. And then for each sample, we are going to store those values, or we are going to take the sample mean and store the sample mean in this x bar vector. Okay, let's run this. And we see that we have some values on the right-hand side, but what we want to do now is visualize the sample mean. And we're going to do that through a histogram. We are going to plot a histogram of x bar vec. Remember the importance of titling your plots accordingly. And here we're going to set the frequency equal to false because we want the density on the y-axis. We also want to overlay the normal distribution with mean mu and standard deviation sigma over root n on top of our histogram. And this mu and sigma come from whatever distribution we are sampling from. In this case, mu is going to be lambda, and sigma over root n will be square root of lambda over square root of n. We're going to be using this curve function where we indicate what curve we want to plot. And by changing the argument add equal to true, it plots that curve on the same plot that we run above. So here we want to plot the normal PDF, which we do by using the function dnorm. And we set the mean equal to lambda and the standard deviation equal to the square root of lambda over n. Technically, if n is large enough, then we should have that our sampling distribution follows this distribution approximately. But if we don't have a large enough n, which is the case here, we'll see what happens. So we want to set the argument add equal to true, and then we'll set the color of the curve equal to red and see what happens here. Okay, so it somewhat follows the shape, but we still have a lot of discrepancies from the curve to the actual values in the histogram. But we set n to be very low. So let's see what happens when we let n equal 50. Okay, that looks a lot better. Central limit theorem has kicked in, and we have much more agreement between the approximate line and the histogram. But I want you to take note of these values down here. So we know that the mean of the sampling distribution will be lambda, and it's going to have standard deviation sigma over root n. So as we increase n, the denominator of our standard deviation is going to get bigger. So the entire standard deviation should get smaller. As we increase the sample size, our sampling distribution should become more precise and more central around the mean. Let's see what happens when we increase n to 500. Okay, now our x-axis has gotten a little bit more precise. We're not going from 2.5 to 3.5 anymore. Now we're going 2.7 to 3.3, where those are the complete outliers of our plot. What happens when we set n equal to 5,000? This will be the last one that we do. Okay, and we see that it's gotten even more precise. So not only does central limit theorem kick in when n is large enough, but our sampling distribution becomes more clustered around the mean, so we have more precise estimates. Now, the final thing we're going to talk about in this video is how to assess normality. Like I said, with a lot of statistical inference techniques and methods, we want and assume that the distribution is normal, and we actually need that in order to conduct some of these methods. So it makes sense that we would need something in place to be able to assess the normality. We can do this through a histogram, even using the empirical rule backwards. So seeing how much of the data is in those 3 percentages that go along with the empirical rule. But a very common way of assessing normality is by using a normal probability plot, also called a quantile-quantile plot, or QQ plot for short. What this plot looks like is you have the standard normal theoretical quantiles on the x-axis, and then the quantiles from your sample on the y-axis. And this plot helps to check if these quantiles are in agreement. If they are in agreement, then you can assume that the normality assumption checks out and you're good to go. If they are not in agreement, so they do not fall on that 45-degree line, then you have to say that the normality assumption is violated and maybe do something else. That is out of the scope of this video. And if you're in my class right now, that is out of the scope of our course, but a very interesting problem. So in order to plot a QQ plot, we use the qqnorm function. And we know that we just plotted the sample means, and because the central limit theorem kicked in, then we should have approximate normality. So let's assess that normality by plotting a QQ plot of the sample means that we just sampled. Okay, like I mentioned, we have the theoretical quantiles on the x-axis. We have the sample quantiles on the y-axis. And if they fall on an approximate 45-degree angle, then we can say that the normality assumption holds. In this case, the normality assumption holds. Let's show an example where the normality assumption does not hold. Let's say we are sampling from a t distribution. We want 500 samples, but my degree of freedom here is going to be 3. Remember, with the t distribution, the degrees of freedom is equal to n minus 1. So in this case, I'm generating 500 samples from a t distribution, but each one is going to have a degree of freedom of 3. So the sample size is, or our degree of freedom is pretty small. All right, let's see what happens now when I plot a QQ plot of x. Okay, so we see that these tails look a little bit different from what we had before. But before, we also sampled 5,000. So let's see what happens here when I sample 5,000. Keep everything consistent. But still, we see that these tails, they're kind of long. There's a lot more curvature. And we do have some agreement on the 45-degree line, I guess, but we can tell that it deviates a lot because of these tails. If we saw something like this, we would have to say that the normality assumption is violated. Now, what about if we sample from a uniform distribution? We already know what's going to happen because these samples are not coming from a normal distribution. The normality assumption would be violated. But what would the QQ plot look like? Okay, so here we do have these long tails like we saw in the T distribution, but the plot does look a little different. We don't have any agreement with the 45-degree line, which should be going like this. And so if we saw something like this, we would say that the normality assumption is violated. Thank you for watching this video. In this video, we showed the central limit theorem in action. Remember, one of the most foundational theorems in statistics, as well as how to assess normality. Thank you for watching.